Welcome to the webinar. The webinar will begin shortly. Welcome to the webinar. The webinar will begin shortly. Welcome to the webinar. The webinar will begin shortly. Welcome to the webinar. The webinar will begin shortly. Welcome to the webinar. The webinar will begin shortly. Welcome to the webinar.
Hello everyone and welcome to the breakout session D presentation. My name is John Howarth and I'm the moderator for this session. The session is entitled Using Variable Speed Drives for Pipe Burst and Pressure Transient Reduction, and it's presented by Martin Richardson from ABB. There will be a short time for questions and answers at the end of the presentation. The presenters' details will be shown during the Q&A session should you wish to contact them for further information. Please post your questions using the Q&A button in Microsoft Teams. We will deal with as many questions as we can within the available time. Thank you. I would now like to hand over to Martin Richardson. Martin, can you please share your screen? That's great, Martin. I think you're muted at the moment. That's great. You've gone.
There we go. I think that should be better. Sorry about that.
Yeah, you're back. That's great. Yeah, you look
Yeah,
good.
sorry about that.
No problem.
Well, welcome everybody, and yes, thanks, John. We're going to talk about variable speed drives and how we can use them to help prevent bursts and prevent pressure transients in networks, and the impact of variable speed drives with regard to reducing leakage, which is clearly a very important subject. We'll wait for questions at the end, and hopefully it will prompt some good discussion. So, starting off with a sort of bigger picture, just some statistics from Thames Water. This was several years ago. They did some surveys from their customers, with their customers, and leakage reduction came out as the biggest issue or biggest preference for customers in terms of managing water resource. Now, of course, it's relatively old data, but it's still relevant, and leakage is a very visual thing for customers. Clearly in PR19 with Ofwat, leakage is one of the key business plan points, so this isn't going to go away, and clearly customers think water companies should be doing more, and us as suppliers should be doing more to help manage resources and reduce leakage ultimately. So it's clearly a big issue, and hence we want to try and help, and we have got some instances where we have helped, so I'm going to talk through some of those today. And look at some of the issues and some of the solutions and things we can put into practice to help reduce the risk. So, sort of categorising leaks into a couple of different sort of areas. There's background leaks, which is what I would call small aggregation of smaller leaks, which are very difficult to detect in isolation, but can clearly add up to quite high volumes because they are there all the time and in lots of places. So you get a lot of these small leaks, and we know there's a lot of new technology on the market. We know there's a lot of innovation going into this area to detect leaks, and some of these small ones can be very, very difficult to find. The more impactful ones, if you like, or the ones that are more obvious to customers walking down the street, as well as the existing systems that water companies will have in terms of the operational data that they are monitoring, are bursts. So that's where we see a significant loss that is very much against the normal sort of flow profile for that network. And obviously, as we can see in that picture, normally they're very visual and exciting. So there's two levels in terms of, let's say, reducing leakage and reducing bursts, and both of them will help to prevent the loss of non-revenue water. When we talk about bursts especially, we are really looking at the impact of pressure transients. So bursts will happen. Where they happen depends on a lot of things. You know, the type of pipe work, the ground in which that pipe work is in, the historical pressure that network has been under, perhaps the users and the load on that network. But fundamentally, the more pressure transients and the higher pressure stress that network is under, the higher risk of a burst. Now, those pressure transients can be caused by a number of things. Generally, we can say valves being opened or shut rapidly, or pumps starting and stopping are certainly significant factors in those transients occurring. Of course, water companies and operators have control over some of these things, but a big industrial plant opening and closing a valve, that's beyond the water company's control, which introduces another issue. Obviously, that kinetic energy that's flying through the hydraulic network as a result of valves opening and closing, certainly non-return valves which are spring operated, that stress and that pressure wave adds to the stress of weak joints or cracks and can only make the leakage worse, which may result in a burst ultimately. So we're talking about pressure transients, which is a very, very short time. So what we're going to do is go on a little sort of journey, starting at the start point, if you like. And I guess up until the last 5 or 6 years, certainly from my experience, there's been very little understanding or real research into transients and why they occur and what damage they're doing. And this is a picture of a logger here, a Triton logger. There's lots of technology development in this area. But what this allows us to do is offer high speed and low speed data gathering at the same point in time. Eventually, many sort of SCADA systems and things will have been pulling the pressure from maybe 1 second, if you're lucky, and really getting the transient data was just not possible because of the technology and the loggers used. So what we can do here is read 1,000 or maybe 10,000 readings per second, which really gives us a better indication and understanding of what pressure is actually on the network at a particular point in time. Now, if we log too infrequently, we're not going to see these events in the first place. So the first thing is making sure that we genuinely have a feel for what is happening on that network. And just as an example, here's just a graph showing the example. The green line is where we would read every 1 minute, and you can see that the line is a linear line because it's been interpolated between 2 measurement points. The red line is if we measure 100 times a second, and clearly with the green line you don't see what's going on in real terms. You don't see the impact of, for example, a pump start and what it's doing to this pressure. So that graph there is over about a 1 minute period. So you can see there's several sort of oscillations happening with pressure on that particular graph. So that's the first thing, is we've now measured what is actually on the network, and most of the control engineers amongst us will know that in order to control something we need to measure it. So that's great. We know what the real problem is now. This is just the sort of introduction of a little case study. Simplified diagram on the right hand side, and effectively this case study is just looking at these 2 booster pumps which are effectively supplying a village. Before the VSDs were installed, it's much like many booster set systems. They're direct online motors, duty standby pumps, and the pumps are started and stopped based on a high and low pressure set point. When the pressure measurement was done, we identified a reasonable number of transient events, and clearly there was enough history of bursts on this network to look to develop and put in place an improvement project. So the solution here was, as you can see on the picture, a couple of VSDs in place of the direct online starters. And this project was purely put in place to reduce the transients. By reducing the transients, the knock-on effect would be that the risk of a burst is also reduced. So there's various things we have to do with the variable speed drives to make sure that we reduce the risk of that transient as much as possible. And one of the things is commissioning the ramp times. There's many theories at the moment about how those ramp times should be controlled. You know, what sort of time delays we need for those sort of the pressures to settle down upon a start and this sort of thing. But generally, the important things are the variable speed drives allow us a soft ramping up and a soft ramping down of the pump. We'll talk about the non-return valves and the impact of that in a second. But what they also allow us to do is to control that pump system on a pressure. So we put a PID loop on to maintain a fixed pressure on that network. rather than having the sort of start and stop limits as per the original system. So we can still start and stop based on pressure. So we still introduce what we call a sleep mode, which is, for example, overnight when the demand is very low on that system, if the pump is at a minimum speed and the pressure is already being maintained, then the system will put itself to sleep, stop the pumps, and then if the pressure begins to drop, then we'll start the pumps up again. The other thing to consider is if the drives are running all the time overnight and we expect a low demand, then we could also start to use some of that data to indicate whether there is actually leakage on the system or not. And again, comparing similar sites could start to indicate whether sites are seeing more duty or more demand than the other similar sites. And again, that can help start to detect these sort of, let's say, background leaks. So if we look at some results from the loggers from this site, very simple picture of the impact that the variable speed drives have had. Just note that the scale is slightly different on these two graphs. But what you see on the left-hand side is around about a 10-minute period of logging, and you can see the positive and negative sort of transients around the sort of duty pressure, which is around about 80 meters. So you can see that effectively each of those transients is because the direct online system is either starting or stopping a pump. So you can see there's been 1, 2, 3, 4, 5, 6, 7 or 8, transients over a 10-minute period. And on the right hand side, when the variable speed drives are in there, we've got a very consistent pressure measurement, no transients, and yeah, much more improved system. Now, the other thing to note at this point in time is the DOL. Those transients are typically caused by the non-return valves operating. So the DOL will build pressure up very quickly. The NRV will therefore operate very quickly, and the NRV operating quickly is more likely to cause a transient on that network. By using the variable speed drives, and I mentioned this before, by commissioning them correctly, we can make sure that we're controlling the ramps very slowly when we know the NRV is going to close, for example. So by doing that, the NRV closing can there's much more clear reduction in the transient by helping to control the way that NRV operates. This is not necessarily the most extreme example we've seen, but you can see on the left hand side, for an 80 meters head system, the peak transients there were at least 1.5 times, almost 2 times the nominal pressure on that network. So what we can say is, what experience has shown us is the number of starts and stops has very direct correlation on the likelihood of a burst on that network. So if you can reduce the number of starts and stops by half, then you reduce the stress on those joints and things by half, and you're effectively reducing your burst risk. So reducing the number of starts and stops is a good idea. And for the fans of the 80s, I've put a picture of Knight Rider on because it was one of my favourite programmes. And just thinking about the wheel spinning concept, starting things aggressively are never going to be good for, let's say, mechanical devices on the network. And here's just some example of 2 or 3 sites where we installed this sort of control. Going from, on site number 1, over 6,000 starts and stops per month of those pumps, and think about those transients that happen every time you start and stop a pump. down to 430 when the variable speed drives were in place. So not only have we reduced the number of starts and stops massively, by over 90% in that case, but we're doing it softly anyway because there's a variable speed drive there. So there's really a double whammy in terms of improving the situation. Some of the sites you can see on those other two, reduction's not quite so severe. Many factors that come into that. Some of it comes down to the design of the pump in the first place with relation to that network. So for example, it's more difficult, or we have to go to sleep more often if the pump is, let's say, too big for the network. So it hits minimum speed more quickly, and then we have to go to sleep. So there's some design and dimensioning aspects that we can learn from this as well, in terms of trying to reduce the number of starts and stops, which should also help reduce the risk of transients. Touch on this a little bit later on as well, but I'll also going to bring in here about the auto change strategy. And a lot of booster sets are duty standby, and the traditional method of auto changing is to stop the pump that's running and then start the other pump. Now, of course, what you get in that situation is your pressure drops and you get several transients of pressure from a lower value. So potentially it's more risky. With the variable speed drives in circuit, I know it's probably a big change in terms of the philosophy, but because we have a PID loop on pressure, there is much less risk of overpressurizing if we start the second pump before the first one stops. In that case, we can keep the constant pressure in the system. We don't have any transients relating to the starts and stops, as long as we can deal with the NRV situation. But the idea is that will help to reduce the transients just by looking at it from a slightly different perspective. So just a summary of that particular project: relatively small investment, including all the loggers, the site interventions and installation, so over £600,000. But the payback of that was very short, around about 9 months, and also an additional energy saving on top. So really been a successful project overall. This is happening elsewhere. Several water companies in the UK with similar sort of programs. And yeah, we kicked this off several years ago, but by the end of this year, the savings as a result of that investment there are looking to total over £4 million. So really, quite simple in terms of there's not lots of hydraulic work to do in terms of interventions. And the key thing there, the pipe bursts has reduced by 90% on those sites where we've put variable speed control in and commissioned them and optimized them. So really good result. Again, some things we just can't stop. If there's 100-year-old pipe work somewhere, then there's going to be a point where it fails no matter what you do. So that's the kind of burst thing. The other aspect of things is just keeping the pressure under control and the leakage that happens because of these small leaks. So just as a bit of an example, a couple of booster sets. Here's the pressure curve for let's say the traditional control. Put some VSDs in, and we can control that, at least that top end of the pressure, a little bit easier. And again, we still will have some start and stop scenarios in there in terms of the control philosophy. But the key thing that I wanted to discuss at this point in time was then when we have the VSDs installed, we have much more control over the delivery pressure of that network. And talked briefly about it before in terms of the overnight situation. Overnight, we have the opportunity, because of the demand, to potentially reduce the pressure set point on that system, which was what this graph's kind of showing, where we've done that. If we look at this curve here, if we reduce the pressure by, say, half overnight, generally speaking, and it depends on the type of leak you've got, but generally you will halve the flow out of that leak. Okay, and it depends on how, if you increase the pressure on some, let's say, cracks, the crack will open more and you'll actually get more flow as you increase the pressure. So that factor is different. But if you take the red curve as an example, it's a linear relationship between the flow and the leak flow and the pressure. So if you reduce the pressure overnight, you're going to reduce the leakage. Just as an example, if you halve the pressure overnight for 8 hours, you're going to reduce your leakage on that network by 1/6 overall. So there's some really simple things that can be thought about, whether you know you've got a leak there or not, to try and reduce it. So yeah, get control. Some hints here. Get control of your pressure. On-off control is not good. We've seen that because of the impact on NRVs and other mechanical stresses. PID loops are great, easy to put into VSDs. You don't need an external controller. Valves, especially spring-loaded NRVs with no control, they're definitely suspect in terms of leaks and bursts. Reduce pressure overnight, and as I say, it's better pressure regulation. We have much better control, and from the sites we've done in these schemes more recently, customer complaints because of pressure issues have also reduced. So just in summary, water loss can be due to water hammer, which is all down to this start, or very much contributed by the starting and stopping of pumps, especially DOL, and the impact that the NRVs have on that system. We know a lot of systems are aging, so there is things we can do with the VSDs to help manage that situation. Certainly the soft starting and stopping with the ramping process is a great advantage. Putting these systems into proper PID control and controlling pressure is also one, because you'll get additional energy savings. Don't forget we can control level, flow or pressure with the drives, depending on the system you've got. And yeah, mentioned auto changing there again. Do we need to start thinking about different methods of auto changing? Now we've got more modern technology, the risk of overpressure situations is massively reduced because we have a PID loop in play. So John, I think that is about time up, and I think we're ready for questions.
Okay.
As I say, if there's anything people don't want to discuss here, then my contact details are up there, and I'm happy to discuss anything if need be.
Okay, we've got a couple of questions in so far, Martin. Let me just have a look at them. Right, the first one is from David. Couldn't the same reduction in transients be achieved by using soft starters to ramp the pumps up and down rather than VSDs? You may see similar results. I would say there's a couple of counters to that. One is soft start. One is the VSDs where we've seen the most success. We've actually put in maybe 2 or 3 different ramps depending on the speed that it's doing. I have to be honest and say I'm not sure if soft starts would allow that, let's say, dynamic ramping. So that would be my first point. Is we've seen some success where we've been able to automatically change the ramp depending on the speed that you're doing. And the second point would be certainly the burst reduction. That the soft starts may help, but getting it into the PID control is also, getting it into speed control is also an advantage. Just to touch on the ramping thing again, when we're ramping down, especially, the idea is we would want to ramp down very slowly in terms of the rate of change when we know the NRV is still open. So we ramp down slowly, and this has some disadvantages as well, which I'll touch on. But if we ramp down slowly, the
the NRV will then come into a close relatively softly, and then we can ramp down quickly to the 0 point. Otherwise, we could be ramping for 5 minutes. If you ramp too slowly and the NRV is not fully closing because you're ramping too softly, that can also obviously give some issues, because you're then backflowing. So there is a sweet spot, and yeah, the commissioning is very important. But yeah, good question.
Okay, next question, Martin, from Mark. Are you working with specific pump manufacturers to put this in place from initial installation?
We certainly, with some of our framework customers, where there's also framework suppliers from the pumps point of view, there has been some collaboration there on sort of standard schemes of a similar nature. Yeah, it's certainly something we're interested in talking about, to increase the benefits for our mutual customers, really. So yeah, there's some work going on there. I think there's still some work to be done in terms of some research. I've put some cases forward for some research for one of our partner universities in Finland to look at some of these details in a bit more detail. So yeah, we would like to do that more, to be honest.
Okay. Next question, I think it's Ziray. Can the VSD be used with progressive cavity pumps, where the pumps require high initial torque and high starting current to start their operation? And can we use soft start instead of VSD just to control the transient during the starting and stopping of the pumps? VSDs seem expensive.
Yes, first question, yes, we can use VSDs on progressive cavity pumps. Most important thing there is sizing them correctly, to make sure that we can handle that initial torque situation. Yeah, I think the soft start question was similar to the first one, if I sort of read that correctly.
Yeah.
So hopefully we've answered that one already. And I guess, yeah, variable speed drives aren't free; they cost money. But I think, you know, we would like to think that with the energy savings and some of these other process benefits, the investment is well worthwhile. And you know, the drive costs generally over the years are sort of staying stable, or you know, in real terms coming down. So you know, that they you know, I would say this obviously, but yeah, they are a very very good investment for various reasons, not just energy. Energy's always been there, but you know, the process benefits are becoming more and more prevalent.
That's great, Martin. I think that's the last of the questions, and we're bang on time. So just like to say thank you very much to Martin for the presentation, and thank you to everybody for attending. I'm now just going to pop up the next slide, which shows the next 2 sessions that are coming along for your viewing. Hopefully you'll be able to make it to those. Thanks everyone, and goodbye for now.